right, so we're doing number 1 here. And it asks us to calculate the force on a spacecraft that is this high up, or this far away from the Earth, and it has a mass of this. Why is there a force of gravity on the spacecraft? I guess it becomes the first question. What do you guys think? Still in the Earth's gravity. I like that. Still in the Earth's gravity. Now, so the force of gravity here is between the spacecraft and Earth, right? Sarah, is that true? Oh, he's working on this problem with me, so I don't call on people and distract from what they're doing. Okay, good. Just to know, so I don't want to interrupt if you're doing independent work. So this is going to be number 1, and the force of, so we might even start off with the gravitational force is between the satellite and the Earth. And Earth. What feature does both the satellite and the Earth have that creates gravity? Mass. Right? So, I might even put after that in parentheses, since both have mass. That's actually one thing I kind of wanted to clear up that I don't think, I think a lot of people didn't get when we were talking earlier, is this idea that if something has mass, it creates a gravitational field around it. And so here's the Earth is here, and it's got all this mass, it's got this big gravitational field around it. And then if we take any other body, a satellite or you, and if you have mass, or the satellite has mass, it also creates a gravitational field. And when those two fields interact, is when there's a force. So to have a force, you have to have two things that have mass, two things that are creating a gravitational field. Those fields interact and create what we call a force. All right? So that's why it's important that both of these have mass. What else controls how much force besides them having mass? The distance their centers are apart, right? So, let's say that. The distance their centers are apart contributes to the size of the force. And there's one other thing that we should remember always about gravitational forces. The race says what we just talked, but they're always attractive. You're on fire today. Nice job. The gravitational force between the two, and I'm going to put it here. Always attractive. Anything else we need in the Y? Force diagram, because it mentions forces. So remember, we've got to use the rubric that includes, let's see, make sure, here it is. It's nice to have that. We have to refer to this rubric here, the one that, because there are forces involved here with this problem. So we want to make sure we show our understanding not only in words but also through that force diagram. So let's do it right down here. So let's see, we've got our two bodies we have the Earth and we have our satellite. And I think I'm going to draw our Earth a little bit bigger. Earth, satellite. And so there's going to be a force gravitationally on the satellite, force gravitational on the satellite due to the Earth, so FGSE, and a force of gravity on the Earth due to the satellite. They're both attractive. Which one's bigger? There isn't a bigger one. They're the same. Good. Nice job. So they're both the same. All right. Now, let's make sure we focus in on what they want to know. Calculate the force, so the amount of it. If it's this far away, kilometers, right away I should think. Change it to meters. Above the Earth's surface, if its mass is this, kilograms. Or change it to grams? No, keep kilograms. Only chemistry likes grams. Everyone else likes kilograms. So they're saying that this distance here in blue is 4 Earth radii, so 4 big R sub E. And then from the center to the edge, that in here would be 1 Earth radii, right? So how far apart are the centers? In my case, 4 or 5, because from the center of the Earth to the edge is 1, and then from the edge or the surface to the satellite for me is 4 more. You probably have different numbers, right? Because if I look, that number's in red. So, all right, let's see. I want to do the how now. Probably be good to grab an equation. And it's gravitational force, so the equation I'm going to grab is the one for gravitational force. Other things I think I might need, I think I'll need the universal gravitational constant. So I'll grab that from the very bottom of our equation sheet. And I think I might need like the radius of the Earth and the mass of the Earth. So I'm going to grab those two. These are all on our equation sheet. So, lots of information here. Let's see. Oops. That. Sorry, just getting all those fun things I grabbed. Let's throw these up here. Okay. So now I'm looking at the gravitational force between these two things. So, F sub G is what I want to find. So F sub G, which one do you want me to find? The force of gravity on the satellite due to the Earth, or the force of gravity on the Earth due to the satellite? Doesn't matter. You guys picked up. Satellite to the Earth. Okay, so SE. And you're right. It doesn't matter at all. Big G, 6.67 times 10 to the negative 11th. Newton meter squared per kilogram squared. Mass 1 would be the mass of the satellite, which for me is 1,600 kilograms. 1,600 kilograms. Mass of the Earth, because that's the other thing in this pairing, 5.98 times 10 to the 24th kilograms. I'm running out of space, sorry. And then the radius, the R, is the distance between their centers. So for me, I'm going to use, I could use the radius of the Earth plus the distance they gave me. I'm going to use the fact that it's 4 Earth radius, so I'm going to use 5 times the radius of the Earth, which is 6.38 times 10 to the 6 meters. And that whole quantity I'm going to square. The 5 is from, they tell me on mine, my satellite is 4 Earth radii above the surface. And I know I have to go center to center. So to get from the center of the Earth to the surface is 1. And then from the surface out to my satellite is 4 more. So it's 5 altogether. What's yours? So yours would be 6 total. Yeah. That will be the most common mistake, is to forget that. Up top, yeah, same as with here. 5.98 times 10 to the 24th. So, number 5. Got these 2 spheres, and they both have mass, so they're both massive. And then, where would you place a third sphere so that the net force on it is 0? So if the net force on it is 0, does that mean it has no force on it? No, they just cancel out. You're right. So if we think about it, where are we going to place it so that it has at least 2 forces on it and they cancel out? You mean like over here? In the middle, but probably closer to A. I would agree. Because can you have forces canceling out if there's only 1 force on it? Okay. Could you, I guess the key that I'm trying to make sure that you get is that the 2 forces on C have to be in opposite directions to cancel out, right? Like the first one we did yesterday with the example problems, right? On particle A, there were 2 forces pointing to the right. There was no way they could cancel out. On B, though, there was one that pointed to the right and one that pointed to the left, so they could cancel out. So I would put something like maybe C will be gravitationally attracted to both B and A, so must be between them so forces can cancel out. And I agree with Sarah that I'm going to predict that it's going to be closer to A since A is less massive. So I might put something like prob closer to A since A less massive. Because for the forces to cancel out, what must be true of the forces? Come on, folks. Forces must be what to cancel out? Equal. Size, let's say, or magnitude. Because we don't mean in the same direction. So then I need my force diagram. Let's put object C right here. Send the page so I can see it better. And then we'd have, let's see, the force and force. And force, and force. This would be the force of gravity on B due to C, force of gravity on C due to B, force of gravity of C due to A, force of gravity on A due to C. And I know that's really small, sorry. But that would be a complete Y. You're showing your understanding through your words and also through your force diagram. Right? And it sketched out how to do our how, because the forces must be equal size. So the force on C due to B must equal the force on excuse me, force of gravity on C due to B, force of gravity on C due to A. Those two must be equal. Now, just their magnitudes, right? Just their size, because we know they're opposite in direction. And then let's substitute in. So we got big G, mass of C, mass of B, over the distance from B to C squared equals big G, mass of C, mass of A, over the radius from A to C squared. And can we cancel anything out? The mass of C gone. Big G's are gone, right? No, because one is from B to C and the other is from C to A. So those are two different numbers. Yeah. But that simplified it a lot. What did they even ask for? "500 centimeters. Should I use this 500? Make it meters, right? So from A to B is 0.5 meters. So that means that RBC plus RAC must equal 0.5. Or no, not half a meter. So 500 centimeters, so that's 5 meters. Right? Oh, so now I've got two equations. One right here, which I'm going to simplify a little bit, and one right here. And a couple of things that I don't know. So let's see if I can get this down to make it look a little prettier, maybe. Let's see. What do they tell me about the relationship of my masses? Two spheres, A and B are, if mass A for me is 2m, and mass B is 6m. All right? So I have mass B, which they told me, I'm going to write this again just so that I can then play with it. That with hopefully less confusion. They told me mass B is 6m and mass A is 2m. So for mass B, rather than I'm going to put in 6m over RBC squared, and for mass A I'm going to put in 2m over RAC squared. Can I, is there anything now that I can cancel out? Anything the same on both sides? What about M? Can I cancel out M? Perfect answer, yeah. 500 centimeters is 5 meters. Remember, I always want to work in the base units. So I can get rid of the m's here. And I hate fractions, so I'm going to make this not a fraction. I'm going to do a little cross multiplication here. 6 times RAC squared equals 2 times RBC squared. Yes? And what was that other equation I had? It was RBC plus RAC equaled 5 meters. Right, so I have two equations here. This one and this one with the same two unknowns. So I could do my fun algebra skills and substitute, right? And do my mathy stuff. Or I can say, I know how to do math, but let me do it on use Wolfram instead. Yeah. Yeah, that was the, they told me that they were 500 centimeters apart. So I'm going to put both of these in Wolfram. I'm going to, yeah, same time. If I put them in at the same time with a comma in between them, it'll solve them simultaneously. Difference is I'm going to use X and Y rather than, so let's put, let's see, marker. Let's put X in here and Y in here. So this will be a Y here, and this will be an X here. 6y squared equals 2x squared, yeah. Yep. Okay, so I'm going to put x plus y equals 5, my first equation. X plus y equals 5. And then I'm going to put a comma, and I'm going to put in my next equation, which is 6y squared, 6y caret 2 equals 2x squared. 2x squared. I do, yes. And I tend to put comma space. I don't know if it needs the space. Then I hit equals. And I look at them and I make sure so they give it to me in exact form because they're mathematicians. If you look in that box, there's a thing that says approximate forms, which is what makes the rest of us happy. And I get negatives and positives. I'm going to go with the two positive solutions because the negative is just a factor of the math. It's not a factor of the physics. So I got x is 3.16987. So you didn't get any of those numbers? 3.17. I'm going to round that too. You got whole numbers? Good for you. I can come by and check your math and see what went wrong, as long as it's worked. 1.83. 1.83. I'm hopeful because mine adds up to 5. So I'm going to try it and see if it works. What is the net force on it? 9 centimeters to the right of sphere B, so that would be RBC. I have it in meters, so in centimeters it's going to be 317. Because I have it in meters, they want it in centimeters. mine work? The math is correct. Let me come around and check yours as needed.